So today we're going to talk about waves, specifically sound waves. So sounds, behavior as a wave, all that fun stuff. So the first thing we're doing is the speed of sound. Now you might notice that there's a graph here because the speed of sound changes. It's not a constant speed. So let's look at the graph a little bit so we can understand what we're talking about. So speed of sound, this is meters per second. If you want to know how many miles per hour, you basically double it plus a little bit. So, 400 meters per second is gonna be around 900 miles per hour. Okay, give or take. That's the rough estimate. But anyways, so what's speed of sound? So it goes between 400 meters per second and 250 meters per second. That sounds like a big change, but you also should keep in mind this is going from negative 100 Celsius to positive 100 Celsius. Now, I don't know about you, but realistically in the world, we're not going to be dealing with temperatures that are in this area or in this area, unless you're into like Alaska stuff or hanging out inside of your oven. But anyway, so normally in like real world language, we're going to be pretty much just in this area here, okay? So around 20 degrees Celsius. So to give you an idea, 20 degrees is going to be around 70 Fahrenheit. Okay, so our speed of sound is going to be close to 340, and it's not going to change very fast. I mean, I hear what you're saying, Mr. Keeney, but it's going to drop, I don't know, 10 meters per second. Yeah, but it's going to take 20 degrees to do it, and this temperature doesn't like drop 20 degrees very quickly. So we're going to keep it pretty much there. Now, some problems might tell you to use 350 or something, just do whatever it says. But for me, you can just think of it as 340 for all that we're working with, unless the problem tells you something special. Okay? Now, some other limitation here is this is all for air. What if you're not in air? Well, then you're in something else. And I want you to notice this. Okay, let's look at some of these numbers. So here's your air right there. But I want you to notice that the material matters way more than the temperature, okay? So if you're talking, you're hearing me, the sound come at this speed. But if you were listening for a train and you put your ear on the rail, you'd hear it coming much faster. I know it's not copper, but it's the closest thing on there. It's coming at thousands of meters per second. So you'll be able to hear the train through the metal of the rail before you'd be able to hear the train through the air, because the sound can travel way, way, way faster. By way faster, we mean this is going to be times 10. All right? And this is always going to be the case. Air is very slow for sound waves, and metal, solids, is going to be very fast for sound, and liquids like water, for example, are going to be somewhere in the middle. So sound will travel faster through water than it will through the air. And we are going to use these, well, especially just the air numbers, to talk about how it behaves as a wave. So we need to talk about the most important wave equation. You might have heard this before in some class, but regardless, here's what it is. So V is equal to lambda F, a very important equation. So V stands for velocity of the wave. So for us, we're going to use metric, which is going to be in meters per second. So it's just how fast the wave travels. All right. Now F should be familiar. F is frequency. frequency is going to be measured in hertz, right? So it's how many waves per second. And this guy right here, that's a lowercase lambda. Oh, I know what it's used for too. But in this case, it's used for wavelength. All right, wavelength is going to be measured in meters. So wavelength is how long a wave is, all right? So I want you to just think about this side of the equation for just a second. You've got something that measures how long it is in meters and something that measures how much it goes back and forth, which is per second. So you're going to get meters per second, which is a speed. All right, so hopefully this makes sense, where the wave is going to be the wavelength times the frequency. Ta-da. All right, so let's actually use this now. So here's a fun practice problem that we'll work on. It's a hot summer day. A pesky little mosquito produced its warning sound near your ear. The sound is produced by the beating of its wings at 600 beats per second. Okay, part 1. What is the frequency in hertz of the sound wave? Well, let's just think about it this way. If it's moving its wings at 600 beats per second, and then the sound waves will be produced by the motion of the wing, it will produce a frequency of 600 hertz. Ta-da! Because it's 600 waves per second. Okay, assuming the sound wave moves with a velocity of 350, what is the wavelength of the wave? Okay, so let's use our wave equation. We have V is equal to lambda F. Do you think you can plug in the numbers to the right spot? Pause the video to try. Did you do it? Oh, let's see. So V is going to be 350, and then that's going to equal lambda times 600. So I'm going to take my 350 divided by 600, and I get 0.583 meters. All right. Now, just to give you a point of view here, that's going to be about 58 centimeters. You don't have to convert the units if you don't want to. It is hunky-dory, but we want to give you a point of view. So this means that every 58 centimeters, the wave is restarting. So there's a cycle there. Okay, this is the goal of this wave behavior. This is a very important equation, and it applies to all kinds of waves, not just to sound. We're just using it for sound right now. Okay, there's some practice. I think it's tied in with tomorrow. We'll see you then.